but it should be good. Okay. Yeah, so we got a little bit behind the original schedule, but that's okay. So yeah, last week I stated the slice theorem and kind of set things up, but then we didn't finish the proof. So that's what we're going to do today. The other thing I did last week, which I want to begin with now, just to review, is I gave a proof of this group action theorem. So I want to state that again now, just in a simple case where I take the group to be C4, to keep things simple, but recall what that says, this group action theorem. So what it says is, well, it gives you a G-algebra description of the underlying homotopy groups of these norms. So this pi star E means the underlying homotopy groups. So this notation BPC4, remember, was the notation for the norm from C2 to C4 of BPR. And this group action theorem, basically told us that these homotopy groups were like G polynomial in the following sense. So we had these C2 classes, the TIs, and then the homotopy of this was generated by sort of that and its conjugates. So what this actually means is that I have a description of this polynomial algebra like this, where first of all, let's say, as usual, gamma is the generator of C4, and it acts in the following way. When I take the square, gamma squared on Ti, I get minus Ti. So this was coming from these induced sign representations. Okay, and just for some broader context here, I mean, what is this spectrum? This is just BP tensor BP, which we already know, is a big polynomial algebra. Its homotopy groups are a polynomial algebra. But this is giving also a description of that, which records how the group acts on it according to this normed group action, which is the one that sort of in symbols looks like this, where the bar is doing this complex conjugation action on BP. Okay, so of course, yeah, writing down this as a polynomial algebra is easy, but this theorem was also doing that in an equivariant way. Okay, so this group action theorem, well, first of all, tells us something about the underlying homotopy groups. So we have a description of say the Whitehead tower, or the associated gradient of the Whitehead tower of the underlying spectrum. And I want to sort of write that out so we can motivate again where this slice filtration is coming from. So let's look at just a few homotopy groups of this. So if I look at pi 0e, this is a Z on the class 1, and pi 2, so this T1 class has degree 2. So in pi 2, I have T1 and its conjugate, gamma T1. And in pi 4, I have T1 squared, gamma T1 squared, and the product T1 gamma T1. Okay, and T2 has degree 6, so through this range we just see the T1 gamma T1 stuff. Okay, so well, let's look at the Whitehead tower of this. So the sort of pi 0 term I have here, and let me do things double speed, so I'd skip the odd associated graded pieces, which vanish. So I have my sort of 2 connective cover, and here I have a S2 plus S2 tensor Z. And in the fourth piece, I have an S4 plus S4 plus S4, which I'm writing separately because the group acts differently on those pieces. Okay, so this is just non-equivariant so far. And the group action theorem, tells us how C4 acts on these homotopy groups. So here, this was a trivial module. this was an induced sign representation. This was an induced trivial representation because, well, when I square a class that generates a sign representation, it's now acted on trivially. And this is a trivial representation. This T1, gamma T1 is this sort of norm class, norm from C2 to C4 of T1. So the group acts on that trivially. Okay, so at least, sort of in a Borel picture, we know also how the group is acting on this associated graded. And the slice filtration is basically the idea that we should be able to provide an equivariant lift of this tower where the associated graded of these pieces are sort of lifted to the correct representation spheres tensor Z underline. So as opposed to the homotopy fixed point spectral sequence where we would have the sort of Borel completions of this, and we would be looking at group cohomology. We're looking at this sort of decompleted Z underline Mackey functor theory, which, as I said, will be something more computable. Okay, so what do we actually get? I mean, we're supposed to be able to more or less read it off from the G module structure. And sort of down here, you'll write it in a different color. The equivariant lift of that one in the slice tower should be a Z underline. And then here I should get it induced regular representation sphere. Okay, and that's sort of incorporating the induced sign action because this regular representation sphere has a 1 plus sigma, so I had one copy of the sign representation in it. And here I have two equivariant summons. I have my 2 row here, 2 row 2, and S row 4. Tensor Z underline. Okay, so the slice filtration is, in a vague sense, just something which is trying to accomplish that. It's trying to provide a lift of the Whitehead tower that sort of gives us these kinds of slices. Okay, so with that in mind, last week I gave 2 definitions of the slice filtration on these BPGs. And now I have to show you that they're the same. But let me remind you of those 2 definitions. So the first, or rather, the second one that I stated last week, but I'm going to state it this time first, was the sort of sequence of T-structures approach that you see also in the original treatment of this. So the slice T-structure is a T-structure on filtered G spectra generated at the nth spot by slice greater than or equal to n is this category generated by all the induced regular representation spheres of dimension at least n. Okay, and so I guess maybe from this point of view, it's sort of thinking like, well, if I think about the Whitehead filtration as being generated in the nth spot by spheres of dimension at least n, then I want to do the same kind of thing to define the slice filtration, but choose the sort of equivariant spheres of dimension n that I expect to see showing up in this description.
What do you write there? Like the cardinality of h greater than n and is greater than 1, or is it k?
That's a k, sorry. So it's a k times, so k is an integer, k times the...
after that?
And that's the same k. So k times the order of h is greater than or equal to n. Yep.
Is there a row here? So in your thing you had the trivial representations and for the fourth guy, and now you put the regular ones.
Yeah, it's because the representation row of C4 is an orientable representation. So like the action on the generator of pi 4 of S4 in this case is the trivial action.
Also, if you restrict.
Yeah. Yeah, that's the reason. I mean, it's also sort of the way we constructed these classes equivariantly. They do have this equivariant degree. But yeah, if you're just thinking in terms of the group action, it's because, if I look at how C4 acts on pi 4e of this, it is a trivial representation.
Okay.
Yeah. Okay, and this gives me a definition of the slice filtration as the following composite functor. So I can take the constant filtration on a G spectrum, and then I can take its connective cover with respect to this T structure. And the upshot of this definition was that it makes it easy to see that it has all the nice monoidal properties we want. This functor is a right adjoint to the colimit functor from filtered G spectra to G spectra. That has a G symmetric monoidal structure, so this is lax G symmetric monoidal. And similarly for this, we sort of checked that this filtration is suitably compatible with the G symmetric monoidal structure, in the sense that, you know, this is a right adjoint to a G symmetric monoidal left adjoint. So this is going to send, you know, G commutative rings to G commutative rings. And that's really essentially the main reason we need definition 1. And I started with definition 2 last week, which is sort of a bit more intuitive from the sort of polynomial description that we saw in the group action theorem. And I'm not going to unravel what this meant again, but the idea was to do some kind of I-adic filtration on BPG, where I was this equivariant ideal here. Yeah. And yeah, that was a bit complicated to define, but we you know, just sort of thought about what a Bachstein filtration should look like, and then normed them up, tensored them together, and got this. Okay, so in order to prove these things are the same, I'm going to need some facts about the slice filtration. So in particular, I mean about the slice filtration in definition 1 for now, because I'm going to say some things about general G spectra, and yeah, I don't have some kind of I-adic filtration for some general G spectrum. I only have definition 1 in general. So I guess the first thing that's nice to know is that, well, if X is a G spectrum, that the slice filtration is a complete filtration of X in the sense that these two things hold. And kind of in low dimensions, the slice connectivity actually agrees with ordinary connectivity. So a connectivity with respect to the standard T structure on G spectra, which is to say that this is the category generated by all induced trivial spheres of dimension n. Okay, and yeah, sorry. Thank you. Okay, this is something which is not so hard to check, and I'll just say that it follows from writing down GCW structures on regular representation spheres, which I'll have to say a bit more about later. So we'll return to it. But I mean, this is the idea is that like these slice categories are generated by representation spheres, and the tau greater than or equal to n categories are generated by spheres with trivial action. And a GCW structure is exactly, you know, putting a filtration on something with associated graded given by sums of induced trivial spheres. And so I can sort of understand these two filtrations in terms of each other explicitly once I write down GCW structures, which gives, you know, this direct comparison, and in general gives some kind of inclusion between connective categories, and from which you can deduce these two things from the analogous facts for the ordinary T structure on G spectra, namely that that's you know, complete filtration. Yeah.
Slice T structure by complete.
As a T structure on G spectra, on filtered G spectra, I think that's true. Yeah. Yeah, I think so.
Could you remind me how to parse definition 1 again? Like, is it a sequence of T structures or just one?
Yep. Yeah, it's a sequence of T structures on G spectra which define a single T structure on filtered G spectra. So in these diagram categories, I can sort of, at each point, ask for a T structure there, and then ask for some compatibilities between them, and then it gives me a single T structure on the diagram category. All right. So in order to prove that these, oh, I need more space. these two T structures in, these two filtrations in definition 1, in this definition, agree, I need to prove some sort of recognition principle for, if you have some complete filtration functor when it is the slice filtration functor. And this is like a really general argument which definitely is not specific to the slice filtration, but I'm just going to give it in that way. So let's suppose I have some filtration of a G spectrum X. I'm just calling it fil X, with the property that, well, it is a filtration of X in this sense, and that I know that its associated graded is concentrated in this slice equal to n category, which I'm not sure if I defined this last week, but this is the intersection of the slice less than or equal to n and the slice greater than or equal to n category, where slice less than or equal to n is defined as this right orthogonal to slice greater than or equal to n plus 1. So if your nth associated graded is an n slice for every n, then you have a canonical equivalence of filtered spectra, a filtered G spectra from that filtration you gave and the slice filtration. Okay, and as I said, it's a pretty general argument. First step is to construct a map. And well, I have by condition 1 some equivalence like this. So I take that map, and that's adjoint to a map from fil X to the constant filtration on X. And condition 2 you can use to show that actually fil X is connective with respect to this slice T structure. So it factors through the connective cover of this, which is the definition of the slice filtration. So that produces me a map, and I need to show that that map is an equivalence now. And the idea is to use condition 2. So here's the argument. So since fil X in degree n and slice X in degree n are both in slice greater than or equal to n, so I sort of claimed that already when I told you I could write down this map, when I claimed that fil X was connective, but that follows from the second condition. Well, then it suffices to show that if I take some generator S hat slice X n, so S hat is some generator of this category, then it suffices to show that this map is an isomorphism. And, well, that's because, these two things are in this category, which means they're generated by, the generators of that category. Okay, so it suffices to show that I always have this isomorphism. And, the idea now is to say, well, when I pass to the colimit in n, since these are both filtrations of X, I get an isomorphism on the colimits. And then what I'm going to show is that actually both of these vertical maps are isomorphisms. And that will imply that the top horizontal map was an isomorphism. Yeah, so we have a map from fil X to the constant filtration, and then we check that fil X is connective. So then it has to factor through the connective cover. Yeah, and I didn't show that, but I'm just saying that it follows from condition 2. Okay. So next step is to say, well, this colimit that I'm taking in these vertical arrows is a filtered colimit. And these S hats I can take to be compact, because this slice n is compactly generated by these induced representation spheres. So okay, I can, in other words, look at the map, let's say on the left for a moment. Field xn. And I can rewrite it as, you know, this colimit here. Okay. Using compactness of S hat. And then all I need to show is that all of the transition maps in that colimit diagram were isomorphisms. And then I'll show the same thing on the right side in the same way, and we'll be done. And the idea is that this just follows right out of condition 2, because I can look in the transition map. So let's just take the first one, for example. And by definition, the cofiber of those transition maps is the associated graded. Fill x. Okay, and well, this is by condition 2, this is slice less than or equal to n minus 1. And so it's in the right orthogonal to the category generated by this guy. So these are 0. And I deduce that these maps are always isomorphisms, and similarly on the right-hand side. Okay. Yeah.
I'm confused. I think you need that this filtration is complete. I don't see where you use this.
I don't think you. So I think that it follows that the filtration is complete from condition 2.
I see.
But I don't think you need to assume it.
No, right, I see.
Yeah. Yeah. Okay. So as a corollary, we now have a strategy, at least, to prove that the two definitions of the slice filtration that I gave on BPG agree. So let's just state this as a corollary. So, well, over here I mean the sort of Bockstein version, and here I mean the T-structure version. Okay. And for the proof that these two things are the same, I need to establish that the Bockstein filtration definition satisfies properties 1 and 2. And 1 is easy. I mean, I think we already discussed it last week. It's just the point that I define these Bockstein filtrations by taking norms and tensor powers and things like that, and all of those things commute with taking the co-limit of a filtered spectrum. And so it's easily checked that this is actually a filtration of BPG. Okay, and for part 2, now I need to actually plug in the theorem that we're going to prove today. So really, this corollary is conditional on everything we're going to prove later today. But anyway, the associated graded of this Bockstein slice filtration as we said last week, was sort of this thing. Okay, it's this normal sort of E1 page of a Bockstein filtration thing where I mod out by the thing and then join it. Here I just have this big, giant G polynomial algebra there. Okay, and well, what we're going to prove in the remainder of the talk is that this quotient here is Z underline. Okay, and that's the slice theorem. But once I have that, then I actually am done with this corollary, because, well, okay, Z is a 0 slice because it's concentrated in degree 0 in the usual T structure on G spectra, and by this lemma somewhere, Where is this lemma?
Yeah.
Oh, here, yeah. That coincides with the zero slice category. Okay, so this is true. And this implies that, also if I tensor this with some induced representation sphere, like something appearing in this summation, then I get a KH slice. Okay. Okay, so yeah, the point is we know exactly what the associated graded of this looks like, assuming that I have this. And then knowing that this is a zero slice, I know that all of the things that I need to show are concentrated in one of these slice categories just are by using this fact and tensoring with the generators. Okay, so that's not so hard, but you need to know this. Okay, and that's something we haven't proved yet. Okay, great. So, well, maybe just as a remark for where we're going, you can also just kind of compute this directly. So you could compute, that this is in this slice category by saying, well, it has to be connective, and then it has to be in the right orthogonal to some list of representation spheres. And being in the right orthogonal to such a thing means that some RO G-graded homotopy group of Z underline has to vanish. And you can also just compute that directly, which we kind of have to do anyway. So let me now move into that part of the story. So this is Bourdon homology. So what I'd like to do for the next section is assume the slice theorem. So assume that we have this equivalence here, and use it to see what it buys us, and along the way define some things we will need in proving it. Okay, so let's suppose we now want to run the slice spectral sequence. We know the E2 page of it, or rather we know the associated graded of it. And keeping things relatively concrete, we really are only interested in the integer graded homotopy groups of our equivariant theories. So, from the beginning we sort of dove into genuine equivariant homotopy because we needed to work there to construct these connective models, EO4, for example, this little EO4. But for the purposes of the Kervaire problem, for example, we just want to show something like the homotopy groups of that thing vanishes in some degree. And that's happening in an integer degree. Okay, so the reason I want to emphasize that is because, well, it tells me that I just need to look at the integer graded homotopy groups of this thing, because I just want to run the integer graded slice spectral sequence. So in other words, in order to compute my slice E2 pages now, I just have to compute things like this. So integer graded homotopy of this. And this goes by another name, namely this Bourdon homology, which is some homology theory on G spaces, which you can compute kind of like you compute cellular homology. But really just what goes into that is just sort of long exact sequences and the following two pieces of information. Well, if I look at the Mackey functor integer graded homotopy groups of Z underline, then I just get Z underline in degree 0 by definition. So I can compute the thing in the line above using that fact and cell structures on S rho G. Okay, and well, cell structures on S rho G turn out to be pretty easy to come by, in particular in this G equals a cyclic 2 group case. So let me just give you some examples of that and then state some facts about these computations. So first of all, let's take G to be C2. And well, the regular representation at C2 is just 1 plus sigma. So I really am asking how to compute the homology of sign spheres. And for that, I have the following cofiber sequence. There's a sigma transfer. Okay, so I'll say some things in a moment about what I've written here, but let me first of all say that I'm giving you a cell structure on S sigma, and this cofiber sequence here comes from just a general construction. If I have a representation V, I can take the unit sphere in that representation, and I can take the collapse map, and the cofiber is the 1-point compactification of that representation, and that works for any representation V. And here I'm applying it to the sign representation and observing that the unit sphere in the sign representation is just the G set C2. Okay, and yeah, here we said we want to compute rho G, and we're just observing rho C2 is 1 plus sigma. Okay, so I've also labeled some maps here. I labeled this A sigma, which I haven't defined yet, but I will in a moment. But the other ones are already familiar, namely this res and transfer. I mean, this res is the map we talked about when we talked about spectral Mackey functors, and similarly with this transfer. I mean, this one literally is the Pointryagin collapse map that we discussed. Okay, so in particular, if you wanted to compute the homology of the sign representation sphere, like in here, then you would be able to do it easily because you know the homology of all of the other pieces and you know explicit descriptions of those maps. So then you just run a long exact sequence, and it's straightforward. Okay.
Is it doable for general
The general computation, I think, is hard. Like to any representation sphere in any group, it is not like some.
No, but for rho G, but it's just like.
So I don't think so. I think just for a general group still that that it's hard. Yeah. I mean, there are things you can say like vanishing regions and things in general, but okay. So now let me say some things about C2 to the n. Namely, well, what does the regular representation look like there? Well, here it looks like a sum. 1 plus the sign representation plus a big sum of two-dimensional representations. So what is lambda j? Lambda j is the representation where I have my generator multiply by e 2 pi I times j over 2 to the n on the complex numbers. Okay, that gives me a C2 to the n representation. And now, if I want to give you a cell structure for this representation sphere, I can use, I can just give you one for each piece and then tensor them together. And for the sign sphere, I use the same one here, using that I have an index 2 subgroup of this thing. And for these lambda j's, that's also not so hard to do, so I'll just tell you what you get. So there's a filtration on this, whose associated graded is the following. So I have a zero sphere wedge. Oops. Wedge these two sort of equivariant cells, where H is the cyclic 2 group of order the 2-adic valuation of J, of order 2 to the 2-adic valuation of J. Okay, I mean, these are just two spheres with a particular equivariant cell structure, and it's not so hard to write down this filtration. And once you do, you can just start computing via long exact sequences in exactly the way I described for sigma. Okay, so let me now state kind of some general things that gives you. So first of all, I want to introduce some classes that you find along the way when you do these computations. So first of all, there's this AV class. This lives just over the sphere. And V is some representation again, and this is just the inclusion of 0 and the point at infinity in this compactified representation. Okay, this is a class we always have. And when V is an orientable representation, I have a class UV in pi dimension of V minus V of Z underline, with the property that it restricts to 1 on the restriction of this, which is just pi 0 of z. So orientable representation just means that the generator acting on this vector space is orientation preserving. So for example, you don't have that sigma is an orientable representation of C2, but 2 sigma is. Okay. So these classes are important, and well, there's sort of a region in these ROG graded homotopy groups which is completely describable, which I want to call the positive cone. And it consists of values of v that look as follows. So I have this sort of basis of ROG in this case, and I want to take the sub thing where I have this restriction on the coefficients. Okay? And yeah, this is a region in which you can describe pi v of z underline really explicitly. And you can also check that this is like a submonoid of ROG in this case. So I can also tell you that there's a ring structure here. So let me say PC is this positive cone, and the result is that this is generated as an algebra by all the A and U's. So first of all, I have A sigma, I have U2 sigma, and I have my A lambda j's and my U lambda j's. The lambda j's are all orientable because they're just like a rotation. Okay, subject to some relations. So first of all, I have that the Euler class. Sorry, I didn't say this. Let me just say this too. I mean, I'm not going to explain how this works exactly, but you can think of these A and U classes as Euler and Thom classes respectively, where I regard the representation V as a vector bundle over a point equivariantly. Okay, that's one way of seeing these classes. Okay, so these AVs are torsion for the index of GV and G. GV is the isotropy group of this representation. So if I think of a representation as a map from G to some GLN, GV is the kernel of that map. So it's the part that acts trivially. Okay, so this relation I have. And then I have these relations that HHR calls the gold relations because they involve the letters A and U. And it tells you how to multiply A's and U's together. So whenever I have an inclusion of GV into GW, then I have the following relation on A and U. Okay, and that's a complete description of the ROG graded homotopy of Z underline, at least in this part. And I sort of commented that here briefly, but I mean, if we want to compute the integer graded slice E2 pages, all the degrees we would care about are concentrated in this part. So we have enough information already to compute the E2 pages of the slice spectral sequence in integer degrees. Okay. Just gonna say a couple things for the break. Yeah.
IV or Z underlying the non-equivariant quantities?
No, the equivariant, just the G part. So I mean, just homotopy classes of maps from SV to Z underline in G spectra. Yeah. Sorry, can you say again? I'm not sure.
So I guess like inside
Yeah.
RO, you
Yeah.
have a locus where the like if you do isotopy separation,
Yeah.
you're always going to get a component that's like integral cohomology of homotopy orbits
Uh-huh.
of some positive dimensional rep sphere.
Uh-huh.
Is that exactly the positive coordinate?
I'm not sure. I think what you say is true for C2, and I'm a little bit unsure if it's true for any other groups, but it sounds, sounds plausible. Okay. Yeah, let me finish in the remaining 3 minutes with just slightly more information about this Z underline and these sort of Euler classes that are coming up here. So this is a point of view that's very important on geometric fixed points, which is that you can view them as a localization. Right, okay, so let's take a G spectrum X now and recall that geometric fixed points is defined as taking the genuine fixed points of this tensor product of X and this space E tilde P. And what is this space E tilde P? Well, it's the one defined by the cofiber sequence like this, where the first map is a collapse map. You take EP to a point. And what is EP? Well, EP is some universal space whose fixed points at any proper subgroup are contractible and has no fixed points at the full subgroup. So it's some universal G space. And actually that sort of defines a homotopy type from which you can see that one model of it is the unit sphere and infinitely many copies of the reduced regular representation rho G, which gives you a description of this E tilde P as a sort of co-limit of n times rho G bar. Okay, but this map from S0 to S rho G bar, this was my A rho G bar. So this is equivalently what I get when I take the sphere and I invert that Euler class. Rho G bar. Okay, so geometric fixed points from this point of view is actually just inverting the Euler class A rho G bar. And, well, either from that point of view or from the fact that this is a co-limit of reduced regular representation spheres, I can compute the homotopy of the geometric fixed points of Z underline. Okay, and again, you have these cell structures. You compute it for every Sn rho G bar and then take the co-limit. And you get this. It's a polynomial ring on a class in degree 2, B. And that class is exactly U2 sigma divided by A sigma squared. So A sigma is invertible because, well, A sigma is a divisor of A rho bar. And I inverted that. All right. So we will need that. And let me just finish before we go to a break with a reminder of something I already said and a slight refinement of it, which is that, well, we know that the geometric fixed points of MUR is MO. And this actually tells us how to compute the geometric fixed points of BPR as well. And the idea is that, when I have this Quillen idempotent, which tells me MUR localized at 2 is a big sum of shifts of BPRs. Well, on one hand, when I forget this to the trivial group, this is recovering the usual decomposition of MU because I chose a lift of the Quillen idempotent. On the other hand, if I take the geometric fixed points of the Quillen idempotent, it is exactly the one giving me the usual splitting of MO into shifts of F2. And so in particular, the geometric fixed points of BPR is F2. And the geometric fixed points of BPG is also F2. Now this involves some formula about taking a norm and then taking in geometric fixed points, which is some general formula that you can check kind of always in the same way by checking that that composite of functors commutes with shifted colimits and seeing what it does on G spaces. And so you will see in particular that if you norm from a subgroup H to G, and then you take G geometric fixed points, it's the same as taking H geometric fixed points. So that's how this description here follows from this one. Okay, let's take a break.